Imagine a workbench with a 3D printer on one side and a shallow box of parts on the other. Inside the box are a few servos, two stepper motors, an Arduino or ESP32, bearings, limit switches, magnets, sensors, and enough M3 screws to assemble almost anything that will fit on the desk. The missing ingredient used to be time. A small electromechanical project could require mechanical design, embedded programming, wiring, motion control, and a simple user interface. Even when none of those pieces was especially difficult, crossing between them could turn a weekend idea into a half-finished box of parts. Frontier coding agents change that equation. Describe a rotating organizer, and the agent can draft a parametric model, export printable parts, write the motor control firmware, create a wiring table, and build a small calibration page. When the shaft is too tight, you measure it with calipers, change one parameter, and print the next version. That does not make the agent a mechanical engineer, electrician, or safety inspector. It makes it a very fast collaborator across several technical languages. So today, instead of following one project all the way down, we are going shopping for possibilities. What useful, strange, or delightful machines could you build with a coding agent, a 3D printer, basic electronics, and a box of standardized hardware? This is AutoIntellect, practical intelligence grounded in the physical world. The toolkit is modest, but the combinations grow quickly. A hobby servo provides controlled movement over a limited angle. A stepper motor trades speed for precise, repeatable increments. A small geared motor makes wheels, rollers, and conveyors possible. Limit switches establish where a mechanism stops. Hall sensors detect magnets without contact. Encoders measure rotation. Temperature, light, distance, current, and humidity sensors let the machine react to its surroundings. The printer connects those components to the real world. It creates brackets, gears, pulleys, carriages, enclosures, bearing pockets, cable guides, and interfaces for objects that were never designed to work together. M3 hardware becomes a kind of mechanical vocabulary. Use the same screw sizes, nut traps, insert dimensions, shaft adapters, and mounting patterns across many projects, and the agent can maintain a reusable parts library instead of inventing every hole again. Code-based CAD is the bridge. OpenSCAD describes geometry in a programming language and can export an STL from the command line. CAD Query uses Python to build parametric solid models and can export formats such as STL, STEP, and 3MF. Because the source is text, a coding agent can edit it, run it, inspect errors, change dimensions, and preserve the entire design in version control. The same agent can work beside the Arduino or Platform I/O toolchain. It can write firmware, compile it, create tests for the logic that does not require physical hardware, and help interpret serial logs when the real machine behaves differently. The result is not prompt to perfect object. It is prompt to first prototype, and then a much shorter path through versions 2, 3, and 4. Let us begin with 3 useful workshop machines. First, a motorized parts carousel. Picture a circular tower of removable bins. Ask for an M3 washer, a particular bearing, or a 10,000 ohm resistor, and a stepper rotates the correct compartment to the front. A magnet and hall sensor establish the home position. The agent can generate different bin sizes from one parametric model, maintain the inventory, and write the indexing firmware. The physical challenge is backlash. If the mechanism approaches a bin from different directions, it may stop in slightly different places. The solution might be a spring detent, a geared drive, or software that always approaches the final position from the same direction. Second, a universal button pusher. A servo in an adjustable printed frame can press the physical button on a camera, coffee maker, garage remote, test instrument, or another device that has no useful software interface. Interchangeable feet, sliding rails, and a compliant fingertip let one mechanism fit many shapes. This is automation at its most literal. Rather than reverse engineering the appliance, build a finger. The important constraint is fail-safe mounting. If the bracket shifts, the servo should miss the button, not hold it down forever. Third, a wire measuring and spooling machine. Wire passes through an encoder wheel, around a guide, and onto a motorized spool. Enter a length, and the machine measures, feeds, and winds it. The agent can calculate distance from encoder pulses, design adapters for different spool cores, and create a calibration procedure. Here, the difficult part is not code. It is consistent tension and preventing the wire from slipping on the measuring wheel. Now consider cameras, where controlled motion produces immediately visible results. A motorized camera slider uses a printed carriage, a belt or lead screw, a stepper motor, and 2 limit switches. The agent can generate smooth motion profiles and a shot planner that turns move 60 centimeters over 20 minutes into exact motor steps. The same components can become a photogrammetry turntable. Instead of moving the camera, rotate an object through a precise series of angles and trigger a photograph at each stop. The result might become a reference model for a broken part, a sculpture, or a tool that needs a custom holder. The interesting design problem is reducing wobble while keeping the platform easy to print. A pan and tilt camera mount adds a different kind of intelligence. 2 servos point a camera toward a person, animal, machine, or area of interest. Computer vision may run on a nearby computer, while the microcontroller accepts bounded angle commands. That separation matters. The vision system can make uncertain observations, but the motor controller still enforces speed and travel limits. An incorrect detection might point the camera the wrong way. It should never drive the mechanism through its own cable. And for the simplest version, remove the tracking entirely. A pan and tilt inspection camera with saved positions could look behind equipment, monitor a 3D print, or inspect a difficult corner of a greenhouse. Not every useful machine needs autonomy. The next group moves beyond the workbench. An automatic greenhouse vent uses a temperature and humidity sensor with a servo, geared motor, or lead screw. The printed mechanism opens a lightweight vent as the space warms and returns to a safe position when conditions change. The agent can explore different linkages, produce a weather-resistant sensor housing, and write the control logic. But software should not be the only way to avoid damage. The vent needs mechanical stops, current limiting, and a way to move manually if the controller fails. A small solar tracker uses 2 axes to aim a lightweight panel. It might follow a calculated sun position, compare light sensors, or combine both. This is a good project for asking whether extra energy from tracking exceeds the energy, complexity, and wind loading introduced by the mechanism. On a tiny educational panel, the experiment is the point. A motorized antenna rotator uses a stepper, reduction gearing, and a heading reference to turn a lightweight directional antenna towards saved locations. The agent can model gear ratios, create a backlash compensation routine, and build a local control screen. The design question is weather. Water follows cables, ultraviolet light weakens some plastics, and wind turns a harmless desktop mechanism into a structural problem. A sensible first version stays indoors or moves only a very small antenna. These projects share a lesson. Code scales effortlessly, but every step away from the desk adds new physics. Now for machines whose main purpose is delight. A desktop XY plotter moves a pen using 2 stepper motors. It can draw patterns, address envelopes, mark drill templates, or turn sensor data into a physical line. The agent can generate the motion firmware, translate simple vector graphics into paths, and redesign the pen holder for whatever marker happens to be nearby. A kinetic weather sculpture replaces a screen with movement. Printed clouds rise and fall, mechanical sun rays open, a pointer shows the wind. Waves become rougher as a storm approaches. The intelligence may live in a forecast service, but the object communicates through shape and motion rather than another notification. An expressive desktop creature uses 2 or 3 servos to move eyes, ears, antenna, or articulated leaves. It might react to sound, the time of day, a finished software build, or the arrival of a message. The agent can create a library of poses and transitions, while ordinary firmware limits speed and avoids jitter. A marble routing machine uses sensors and servo gates to send marbles down different printed tracks. The routing could follow a game, a random process, or live data. Perhaps one path represents solar generation and another household consumption. Suddenly, an abstract number becomes a physical event rolling across the desk. Finally, a modular rover provides a reusable moving base. Two gear motors, a motor driver, a battery, and a simple chassis become a platform for a camera, environmental sensor, drawing attachment, flashlight, or tiny gripper. Instead of building a new robot each time, ask the agent to preserve one mounting interface and generate a family of attachments. There is one more category: small machines that make other projects easier. A motorized turntable can photograph every new printed part for documentation. A servo-driven gauge can repeatedly test how far a button or spring moves. A component counter can use a light gate to count screws or beads passing through a printed chute. A simple winding jig can wrap coils, cord, or thread with a repeatable number of turns. These may not look like robots, but they are often more useful than a robot. They transform a repetitive hand motion into a controlled process. This is also where a coding agent earns its keep. The mechanical idea may be one motor and one sensor, but a finished tool still needs calibration, saved settings, error messages, documentation, and perhaps a small interface. An agent can build those surrounding pieces without turning each one into its own software project. A productive prompt resembles an engineering brief. State the goal, identify the parts already available, provide critical measurements, list constraints, and define what success means. Ask for a plan before geometry. Ask which dimensions should remain parameters. Ask the agent to compile the firmware, render every printable part, and report the checks it actually performed. Then bring the physical evidence back. A photograph shows cable interference. Calipers reveal that a 6mm shaft is really 5.8. A serial log captures a missed limit switch. The agent can revise quickly because the design, firmware, and documentation live together. The conversation becomes a record of why the machine took its final shape. Before choosing a project, apply a simple feasibility test. Can most of the structure be printed without heroic supports? Does it use common low-voltage electronics? Can it be assembled with familiar fasteners? Are there only one or two important axes of motion? Does a sensor confirm what the mechanism actually did? If something fails, is the result a stalled carousel rather than an injury, fire, flood, or escaped animal? Servos can pinch and draw a surprising current when stalled. Stepper motors can remain hot while standing still. Printed parts weaken across layer lines and can creep under continuous load. Batteries, heaters, mains electricity, heavy loads, and safety-critical equipment move a project into a different class. Use fuses, appropriate motor drivers, separate power where required, hard travel limits, guards, and a physical way to remove power. Make the safe state the default. Let the coding agent propose calculations and tests, but verify component ratings and mechanical loads yourself. Most importantly, keep generative AI on the design side of the boundary. The agent can create geometry, firmware, documentation, and experiments. Once the machine is running, deterministic code should control motion, enforce limits, and decide what happens when a sensor fails. That boundary does not make the process less magical. A few years ago, the ideas in this episode might each have required a different tutorial, a different software environment, and several abandoned starts. Today, one person can describe a mechanism, generate a first design, print it, wire it, test it, and return to the same collaborator with a photograph of what went wrong. The most exciting project may not be any item on this list. It may be the oddly specific machine that only you need and that no manufacturer would ever build. Look around your home, garden, or workshop. What repeated motion, awkward measurement, misplaced object, or small annoyance is waiting for a motor and a printed bracket? This has been AutoIntellect, practical intelligence grounded in the physical world.